We also have two discussion meetings. One was yesterday, and it was incredibly productive and useful. It was so productive that we decided the one tomorrow to start 1 hour earlier at 10
Was it
o'clock.
recorded so I can steal some of the ideas, or
Huh?
was it recorded? Was it recorded?
No, it was in the discussion room. And because we came across this sort of stuff in our conversation, so we asked Doug to give a short talk on the landscape problem, which is related to computation of spectra of Schrödinger operators with high oscillatory potential, starting at 10, and then we'll have our discussion, and everybody is welcome. It is in the discussion room. So the speaker today is Carolina Lasser from TU Munich, and she'll be trying to catch a wave.
Thank you. So the idea is to do it in joint work. It's not only me who wants to catch it, but all of us, hopefully. My schedule is very light, and there's a wonderful blackboard, and whenever things become unclear or you would like to know more, please just interrupt and I'll try to work a bit on the blackboard. Since the audience is rather diverse somehow, I'm trying to be quite elementary, and for some of you parts might be rather boring and some might be a bit not understandable, so please give me a chance to correct and somehow go on mean in a good position. So it's about Schrödinger operators. We have a Laplace operator and we have a potential V. So Hermann had a very good stick.
Here.
There, yeah. Right in front of me. Good. So, potential V. And the potential is a smooth and nice function, a Born-Oppenheimer surface. I will comment on it right on the next slide. And the other noteworthy thing here is the mass of the nuclei. Of course, if you have a molecule, there are several nuclei. Everyone has different mass, but to keep life simple, we just put 1 M here. So I'm going to do asymptotics to that problem here. And there will be a small parameter in the game. And physically speaking, the small parameter is something like 1 over square root of m getting very large. But, and usually we then write epsilon for that quantity, 1 over square root of m. But there's another person, somebody from the other camp, who uses epsilon squared, where I would put epsilon. So, therefore I decided to go for something else. We have kind of set up as a kind of peace treaty between the different camps that we always use an h bar instead of that. So whenever my tendency would be to put an epsilon, we stick to the h bar, and then somehow with this compromise we somehow become a bit unphysical, because h bar is a physical constant, it should be 1. So I work around in the other way. I put the M1 and I play with the H bar, but you can be assured the bookkeeping and everything is correct. Whenever I have an H bar somewhere, there's always a 1 over M hanging around, and things can easily be converted. It's just a matter of what I used to think for your bookkeeping, and I hope that the H bar solution is quite okay for us today. Okay, so Schrödinger equation, the D is large, so somewhere between 10 and 20 as a kind of routine setup. Of course, one would be happy to go higher, but it's moderate high dimension. It's not this super huge dimension of millions or whatever. But nevertheless, D is large enough such that your backbone reaction to come with finite differences or finite elements or whatever is definitely not appropriate. Yeah? So we have to do something. Okay, D is large. H bar is small. And the potential function comes as the output of an approximation you have done beforehand you start working. So the rationale is the following. In a molecule you have two main players that are the heavy nuclei and the light electrons. And due to that mass discrepancy, there also comes a discrepancy in velocities and when moving around. And from the perspective of an electron, a nucleus is somehow, an atom is somehow static. Yeah? So from the perspective, from the electrons, you may fix the nuclei at whatever position you think is appropriate. And then from the perspective of the electron, you solve typically the eigenvalue problem. Clamped nuclei, and then you have a Laplace in the electronic coordinates. You have a huge Coulombic interaction potential between electrons and nuclei. The nuclei are fixed at position x, and you solve this big, huge electronic eigenvalue problem for one position x, which is a huge problem. There's a huge industry, a lot of incredible manpower going into that for decades now, for solving the electronic eigenvalue problem. And then you have produced a number, V of x. And this is, of course, not about chemical reactions or molecular dynamics. Now you have that single number. And at the end of the day, when we think about molecular motion, we want to see the molecule moving, and it's about the movement of the nuclei that we want to see. So then we come again, we say, okay, what is if the nucleus is somewhere else? Clamp. Solve the huge, enormous problem. And that way, you construct a function that is called a Born-Oppenheimer surface or a potential energy surface. You can prove that those functions are smooth and analytic away from certain crossing points. We won't touch them today, but generally speaking, the V is a smooth and nice multivariate function. However, super expensive to evaluate, because every call for a certain position x comes with tremendous computational effort. So there's now two approaches in the chemical community to that dilemma. Approach number one is to construct such surfaces mainly by theoretical reasoning. You do some a priori assumptions, you put some building blocks like Morse functions, polynomials, whatever. You cook up a cocktail, kind of an analytic form, and then you do a parameter fit to solving that. So then you choose selected point, nucleonic positions of interest, and then you do a fit of your ansatz to what the actual electronic eigenvalue solver gives you as concrete numbers. And this is kind of these empirically constructed potential energy surfaces where a lot of theoretical gut feeling gets in the modeling, and then there's some kind of coupling back to the electronic problem where the parameters are then actually determined. And then you have a very nice and smooth function V. You can easily evaluate. Usually it's a closed form expression with a tons of parameter, but these parameters are in tables, and you can evaluate those functions super quickly and nice. This is the one line of thought. The other line of thought is that you don't trust this procedure I've just described, and you go for numerical methods that do not require a fully mapped out surface, but are kind of so basic that it is just function calls, and then you can evaluate. And then it's just one value you need, and then you move on, and then you ask again. But the idea behind those direct approaches is that there's rather few evaluations of direct electronic structure code, but very few of them. And then it's not really that you have a full surface at your hand. You also need to store it, etc. Right? It's a rather lean procedure. You just go on the way, you evaluate. But yeah. So what I'm trying to present here is methods that go in the second class. I'm trying to analyze possibilities, but I pretend from a theoretical point of view that there is the function behind. Yeah? So when I say potential energy surface, I mean a theoretical construct, somehow the function, but I don't pretend that I really have this fully mapped out high-dimensional surfaces. So I put in red all the scientifically critical parts of my talk. So when I write here the solve, it's not a naive solve. I'm totally aware that this means a lot of work. Yeah? So I mean, we discussed that on Monday. Typically, one surface construction of a certain type of molecule is one PhD thesis. Yeah? So it's something you have to be very careful with. It's not okay.
So the Kayavaks, those are electronic wave functions of Y, right? They're
Exactly,
functions of Y.
and they depend parametrically on the x.
And here, you are interested only by the ground state or by the...
For the moment, today I just will be in the ground state, or maybe I'm somewhere up, but I'm up in a sense that I don't see the other ones.
Because in fact you have a whole family of V.
I have a whole family of V, and then the real fun starts, or as you said yesterday, the real love killers are there. For the moment, I just want to go on one surface. I pretend there is nobody else, and I just elaborate on what we can do on one surface. Okay? Good. So, I write the corresponding evolution equation, the Schrödinger time-dependent Schrödinger equation in that form. The Hamiltonian operator is a Schrödinger operator, Laplace plus a potential. The potential is nice, has smooth, good growth conditions. So the Hamiltonian is a self-adjoint operator. The self-adjoint operator, I can associate a unitary group, the exponential of ith, and I will use that propagator for writing my solutions, but I will also take kind of a complementary point of view. I will not only use the propagator acting on wave functions, but I will also use it when acting on observables, on operators that go on the wave function. So, but I will come to these points later with much more detail. This is just a fixed notation. Okay, and this is kind of my way of thinking about the wave packet. I mean, the color may change how they move, but the point is it's highly oscillatory in high dimensions, so this is 2. Or I don't know if it is but, at the end it turns out as an advantage, but if you formulate the problem at first hand, it might seem as a difficulty. highly oscillatory, well localized. So it's little fluffy localized carpets that are running around in high dimensional spaces. And at first sight, you think this is impossible to do, right? High dimensions, and you want to catch tiny oscillatory pieces. The point is that both things that at first sight seem difficult, namely the oscillations and the small support, turn out to be your rescue at the end of the day. For those type of methods, I will show you the oscillations help, the localization help. Because we are not really screening the full space for something, we are somehow starting with the initial datum, and then we are following. And this kind of, for that reason, localization and oscillations are quite good. Localization is good for following somebody who's small, and oscillations is somehow also very good in the sense it doesn't, you do not want to be super accurate. I mean, I don't want to resolve every hair of the carpet. I just want to know what is the rough profile of the carpet, and then things become somehow a bit regular. Okay, so the formula behind that carpet, that yellow carpet, we had a Gaussian amplitude. So the oscillations come from that linear term here at the end, that plane wave term. The P is the momentum vector that tells you how fast this stuff oscillates. Then we have here this Gaussian amplitude in front of it, and it is written in a weird way. It's a quadratic form, and the quadratic form comes with a matrix that was called PQ inverse. The matrix is complex symmetric and has positive definite imaginary part. So having positive imaginary part with an I in front of it tells you that we are actually exponentially decaying. So we have a very nice Gaussian function, but being a complex matrix, we have actually more than this exponential decay. We also have something that goes on in terms of quadratic oscillations, if you want. And the good way of touching such matrices that are complex symmetric, have positive imaginary part, is a factorization in the form PQ inverse. And those two matrices, capital P and capital Q, will satisfy the property if you pull out real imaginary parts, the resulting thing is a symplectic matrix. So there is a correspondence that every complex symmetric matrix with positive imaginary part can be written this way, and vice versa, given a pair PQ in P and Q, putting such that the real part, imaginary part is symplectic, I get somebody who is complex symmetric with positive definite imaginary part. But be aware that thing is not unique in the sense that if I put something unitary in front of P and Q at appropriate places, it doesn't change the outcome. Yeah? So up to unitary multiplication, such a factorization is unique, but it's not really unique. Right? Okay, so this will be extremely helpful for adjusting the size of the carpet in a rather elegant way. So I've written that slide rather in particular because there are some parts in the community who don't do it like that. They keep the C as it is, and I would really advocate for going for the PQ inverse. And you can already smell, I mean, having symplecticity in the background is something very nice in terms of structure preservation. Okay, so what will I use for moving those carpets? The center of the carpet will move with classical Hamiltonian equations. The width matrices will follow the linearization of the flow, and on top of that I will have the oscillations that are described by the action integral. Okay, so that was kind of the prelude, where I somehow show you what we have, the carpets and the instruments I'm going to use for following these carpets. And I will now address two methods of doing it. The first one is are the Gaussian beams. So I'm not 100% sure if this Royston paper from the 80s is really the first source, or maybe there's earlier one.
Yeah, there's also seismic wave community.
Yeah, so but at least somewhere in the
Mathematical, not mathematical.
so somewhere in the late 70s, early 80s. So that Gaussian beam business started. One of the matadors is here in the last row. So you see several papers by she on the topic, and I also did a bit of it. So we start now with the simplified setting. We forget about the size of the carpet. We just ask ourselves, standard size carpet, moving it around. We don't care about the size for a moment. So I have here just identity and the oscillations. And now comes something very beautiful. Those Gauss functions that are oscillating form something that has many names. You can call it a Gabor frame, an overcomplete set. You can call the formula that is written here the formula of a continuous wavelet transform, or whatever. I mean, you already see there are many names. It's a rather fundamental statement, but it somehow has not really canonized. Different communities use it, and use it with different names and different applications later on. So the proof of this reconstruction or inversion formula is a two-line computation using Fourier inversion formula. You have in your wave packet this Fourier factor. You plug everything in. You do a one-line modification of the integrals. You apply Fourier inversion, and then you are done, and you come out here. So you can also see this integral here as a kind of manifestation of or a continuous version of being an orthogonal, of being a basis somehow, right? Those Gaussian functions, they are not orthogonal. So if we would have here a finite sum for an orthogonal set, it would be the usual thing that you say, okay, the expansion coefficient is the inner product, the basis function with the guy I want to expand. And here we have the family of non-orthogonal functions that together conspire and in a continuous superposition or integral are able to represent any reasonable function. As a corollary, out of the inversion formula, you easily get this Blancherel type statement that you get the norm of somebody by integrating over the modulus squared of the expansion coefficients. So these are kind of the two main tools. The fundamental one is the inversion formula, and the other one comes as a very, how do you say, as a very good tool on top of it, because you're in full control of the norms all the time. Even so, the guys are not orthogonal to each other. But as a collective, they are extremely smart and sit exactly on the norm of the function they are decomposing. So this is quite, I don't know what to say, I think it's quite deep, right? I mean, it comes very quickly, you prove it within 2 lines, and you believe in Fourier inversion, but the consequences are really drastic. It's extremely extremely cool.
Can you put up the formula for GZ again, the previous
Oh
slide?
yeah, maybe I write it on the blackboard since it is so. There's even white. So the GC. To keep it normalized, I have a pi factor in front, and now I have here the quadratic part, which is of unit covariance, and then I have oscillations like that.
Because my question didn't go away. What is Z?
The set, sorry. Yeah. The set is the phase space center. Both of them together.
Z is QP.
Yeah. It's really both. You work completely in phase space. You're shifting, you're scanning all possible centers for the amplitude, and you're allowing for all oscillation frequencies. You can also see the formula, the inversion formula, as a windowed Fourier transform or short-time Fourier transform statement here. If you don't like saying wave packet or gamma, you could say this is the inversion formula for short-time Fourier transform having a Gaussian window.
You're just saying if we plug this formula into that formula and use Fourier inversion,
Exactly.
that's all we need.
Yeah, it's extremely simple, just one line. Would it build up confidence when I do it, or is it?
I believe you.
That's okay. It's already just, I mean, you do Fubini, etc., so you first argue on Schwartz function. Okay. Good. Now, activating backbone reflex. Every integral is a sum. Every integral wants to be represented as a sum at the end of the day. For the moment, just forget how I choose my quadrature points. Yeah? Let's just say I do some reasonable quadrature to the integral here in the inversion formula, and that means that I can see the integral here as a device how to build up linear combinations of different wave packets to represent an arbitrary function. Yeah? So, and the coefficients are the integrals of the wave packets. It's the function I want to represent, and the weights I get from the quadrature I choose. So for the moment, let's forget about what quadrature to choose, just to show you when I do this in a Monte Carlo fashion for a 1D wave packet. I have one of those guys and I ask the question, what do they think as a collective about that individual one? Let's represent him by 10 well-chosen other wave packets. And then this is just the real part of a 1D wave packet. So you see when you do a Monte Carlo, very plain and basic, you get something like that, which is already quite convincing in terms of the center and also somehow maybe not so good on the tails. So you are
What do you mean with Monte Carlo here?
So Monte Carlo would mean here when I have my integral. The idea is I do equi-weighted quadratures of, so I write that integrand here as times modulus. I put in some normalizing factor. Constant here, such that I get a probability density and run I'm sampling from that probability density here, and I keep all the rest as an integrand. So 10 sample points here, 100 here, so now we're quite fine. You see the oscillations on the tails quite small, and I think this is super decent. 100 points. I mean, super decent, not for people who go to the 6th digit, do subnorm analysis and want to go to the 6th digit. Of course not, right? I mean, I have all that stuff here in mind. I'm looking at a one-dimensional situation, having in mind that I want to carry on in 10D. And that at the end of the day, I will produce, let's say, 2 somehow reliable digits at the end. And when I'm here, I feel quite safe for entering. Because here, I mean, there's always some dimension dependence in the variance. When I do Monte Carlo, so dimension is never completely out of the way, but at least there is no general obstruction to move up and to be confident about the results. So, we want to propagate a wave packet. We use the inversion formula, go with the propagator on the individual wave packets, and then say, okay, individual wave packets are quite nicely moved around. The ingredients I showed you earlier, moving the center along a classical flow, adjusting the width according to the linearized equations of motion, putting in front of it an action, is a decent approximation. Why not use it for everybody in the integral and then do the collective integral for all? So this is the idea of a phase-space based Gaussian beam ansatz. And then the interesting thing comes that even so in this in this Gaussian beam ansatz, everybody is somehow autistic, right? Every Gaussian function is moving by himself, own center, own width, own action in front of it, no coupling, yeah? But together as a team, even though they don't look at the others, there is something in the air about collective oscillations that renders the approximation more accurate than if everybody would have gone by himself. So if I evolve Gaussian wave packet classically in the way described, my approximation quality is square root of h bar. And when I send the swarm, I go up to an h bar. And this makes a huge difference. When I think that my small parameter in the game is somewhere around 1/100, which is, as a rule of thumb, quite safe for molecules, a square root of h bar, this is 1-digit business, whereas a plain h bar is already another digit, right? So this brings you somehow into the game. And interestingly, this construction, I mean, has been around since the late 70s and 80s, and it was always clear that the beams together are better than everybody individually. When you look at all the papers, the papers concerned with accuracy, they always say you can only prove square root h. And I think the first proof that you really have the plane h bar is from 2014. Somebody I never met, Cheng, Maybe you know how.
Using Tsinghua University in China.
And then later there was an alternative proof by Leo and Olafur, Mark and Technische. But both different methods have WKB initial data. In the proof of Zheng, you do a very heavy WKB analysis with matching and gluing, and also the Rundberg proof is quite heavy in terms of oscillatory integrals, Taylor approximation, cutoffs, etc. And we have a new proof that is much more simpler. And it goes for general initial data. It's a Fourier proof. Jumping on that short time frequency point of short time Fourier transform point of view, I have outlined in my discussion of the inversion formula, and you get the same thing for arbitrary initial data. And what is also quite nice, that tells you that you're not only safe, or that this approximation is not only good because you are wildly oscillating. It's not just a small parameter game, it's more. It's actually also something that the approximation is exact as long as everything is quadratic. So we are actually picking up for the arrow only non-quadratic contributions of the operator, and then these non-quadratic contributions scale favorably with the h bar, and therefore we have a small thing. But it's not just that I desperately need an h bar in the game, right? It's a good way of non-cubic remainders popping up, and then the small parameter, which gives you accuracy. Good. And then we do a particle method out of that theorem. We choose, so again in red, given the coefficients, if you can do them on paper, you're fine. If you have to really do it numerically, you have a horrible oscillatory d-dimensional integral to solve for the position set. Assume somebody gives it to you as a present. Choose quadrature nodes, simulate the classical dynamics, sum everything up at the end of the day. Embarrassingly parallel, super. Okay, so what we have so far, we have a way of discretizing the unitary evolution by an error which is order of h bar. Unfortunately, we have nothing here. So when you, you are exact in the quadratic case. So for harmonic oscillators, you're very nice, you do the right thing. But as soon as you have potentials with normal potential, with cubic remainders, you're off the hook in terms of mass conservation, in terms of energy conservation. It's kind of not the thing you would like to do for geometric numerical integration, right? It's just about accuracy, not about structure. So we are unhappy and do something else. Something else has been around again in this is now the chemical literature. Bill Miller from Berkeley, Eric Heller from Harvard, and in the mathematical community, nobody, let's say, in the analytical community, people knew it by heart, also since the 70s, but the numerics community ignored it completely. Why? So the reason why it was ignored is that you need pseudo-differential calculus to understand what's going on. And the idea is now to do a 2-minute crash course in pseudo-differential calculus that you don't mind anymore if somebody says quantization. So this is the idea now. So I want to propagate some operator by a unitary evolution. And I call the outcome A of t. So this is the program, and the program is to understand who is A of t. So first thing is for understanding operators, let's say from the point of view of quantization. So the dream is I have a function on phase space, position and momentum, and I have a controlled way of associating operators to those functions on phase space. And then there is a principal dilemma. For position, so for Q, I take multiplication with Q. For momentum P, I take a derivative. Both don't commute. So what to do? I mean, for a function on phase space, I don't care about ordering. If I multiply by Q and then by P or vice versa, nobody cares. But I care a lot whether I multiply first and differentiate or vice versa. So there's a problem. I'm somehow trying to combine structures where one of them is inherently commutative and the other one not. So the suggestion by Weil was, if you don't know what to do in terms of the ordering of multiplication and differentiation, why not be democratic and do all the orderings and take the mean? I mean, why not, right? If you don't know, just go for the average. And then, surprisingly enough, if you now follow that program, you get to Weil quantization. So polynomials are quantized by this democratic approach. All orders are taken into account. Once you know how to quantize a polynomial, again, I mean, I'm now quite brutal, but an exponential polynomial somehow. So I know how to deal with nice analytic functions, in particular, what to do with the exponential function. And when I know what to do with the exponential functions, then I'm going to do Fourier transformation. I do use Fourier inversion formula, and then I lift everything up to functions that I can represent via Fourier inversion formula. I love that. So this is kind of one approach, which is quite down to the earth, and it brings you can work with all that if you do it like that. You don't need to talk about simple classes and all the other things. You need to know the basic democratic approach for the polynomials, and then you go on. Okay, good. So once you are convinced that Weil quantization is the natural thing to use, you start playing with your operators. So I have some operator and I want to look what do we get in time when we have a solution of the Schrödinger equation in the inner product. I write the solution of the Schrödinger equation as the unitary propagator applied to the initial datum. I put the adjoint over. We just discussed that we are confident of putting all that together in one operator we call A hat of t. And then we have, so what I have done on that slide is the passage from the Schrödinger point of view where I evolve a wave function to the Heisenberg point of view where I evolve an observable. So being confident about observable evolution, I dream that I can represent that inner product as some function on phase space related to the initial datum plus the function on phase space that is the symbol of my operator. And
What is the notation here?
which one?
I mean, what do you mean by this bracket with the...
With the two lines. Oh, sorry. This is okay. So you would prefer probably commas. So when I write that, or I could omit. I mean, this is the bracket notation. I could omit one of the lines here, or I could also put
And this is just an inner.
Inner product. That would be better.
Much better.
No, this is what
So
is
physics,
not,
not-
physicists call it the bra and cat notation.
Yeah.
And it
This
goes
is
back
bra,
to the
and
Iraq,
this is
so
cat.
we are at the right place.
It's quite gives you pain, right? What's wrong with bra?
Does more to keep physicists and mathematicians unable to talk to each other.
Yes.
Than anything else.
That's very effective.
But you know, at the end of the day, it's just about putting a, how do you say, a line as a comma. And it has, I mean, it has some advantages. You know, I mean, again, this is somehow sitting on this wave function, on the Schrödinger representation. We're talking about wave functions and inner products in an open space. And when you use the bracket notation, you can do matrix mechanics. You can think about him in the middle. You are all
Yeah.
it's
The
not so
trick
bad.
is, whenever you give a talk to physicists, use the mathematical notation. When you give a talk to mathematicians, use the bra and cat notation, and everybody will think that you are very sophisticated.
So I did the right thing.
Exactly.
But I would like to demystify, really, it's just turning a line into a comma or vice versa.
Okay.
If you want to be a physicist one day, you just put it.
Well, the physicists think of the bra as being an element of the dual space.
You invoke Rees representation
Right,
theorem.
this is
and-
going on there too.
Yeah. But really, I think I have learned to appreciate that way because it somehow helps you thinking about him in the middle, separated from the rest. It's not so stupid. Huh?
They've gotten to you.
Yes, after decades, right? But I have not converted. Good. So now we are all sophisticated because we are able to erase lines into commas and vice versa. We look
Just a little bit more. so you
even
can
more.
just
This
post
is
up a
still
bit.
up.
Yeah.
Okay. So this was our motivation here. We said, okay, expectation values, we write them as a phase space integral, and that all this is really solid. So this three-step program about polynomials, exponentials, Fourier inversion gives me wild quantization. At the end of the day, when you work it out, you get an integral kernel representation of the operator having a function A on phase space. You have this symmetrized evaluation in terms of there's the psi missing in the formula. There's a formula psi of y.
Yes.
So imagine there is a psi of y. So you go from y to x, and the observable is evaluated in the middle. You can also think of it as a convolution, and you have this Fourier transform on top of it with respect to the momentum. It comes out. I mean, when you do step 1, 2, 3 and work out, you get that. And then when you go back to the wish list of the previous slide, when you say, I want to write that here as somebody, kind of the symbol of that operator evaluated against some transformation of the wave function, similar calculation, it tells you you have to take the wave function, you go a bit to the left and to the right, you do a partial Fourier transform, and that's the thing. Again, one line computation, nothing difficult at the end of the day when you want to compute. Okay, so you see, everything is under control for people who are able to integrate and take a Fourier transform. Okay, and now the idea is to be even more simpler than we were before. And we were already simple before, where we said those carpets move along classical dynamics and they breathe according to the linearized equations, and they have this action integrals in front of them. Now we move the symbols of the operators just along the flow. So from the 3 building blocks of wave packet motion, we throw away 2 of them, and 2 of them are actually are a bit painful, right? The action integral brings oscillations in time, maybe difficult to resolve. The movement of the carpet tells you need the linearized equations of motion, you need the Hessian of the potential. In practical applications, people might just send you out of the room when you propose to use the Hessian. So just moving, just the center motion. And when you do that way, when you're just sitting on this classical motion, you're directly harvesting everything you could dream of in terms of conservation. And you ask about mass non-conservation, you're talking about a Hamiltonian flow that is plainly evolved. Fully. Energy, same thing. I'm just doing a Hamiltonian flow and nothing on top of it to destroy it. Sticks, just by the very construction. And on top of that, there's Egorov's theorem that tells you that due to all the symmetrized setup of the whole game, it's like if you move from Trotter splitting to strong splitting, or midpoint rules, or whatever way you like to think about symmetry and discretizations, you get 1 more power for free. Yeah? So suddenly you have an h bar square there, which is more than you could ever dream of, right? By being super simple, using the simplest block of all the game, but using it in a symmetrized way. Yeah? You're right on spot with the simplest block you have. And again, exact for harmonic oscillators. And again, one crime, I pretend that I know the Wigner function of the initial data, and then I do the same thing, even more simple than before. Choose nodes, I involve them as a classical flow, and then I weight everything with the initial Wigner function value, sum up, end of the day. Extremely simple. All what I've shown you are laptop computer algorithms, right? You don't need embarrassingly parallel. If you want, you can parallelize, but maybe you don't even need to, right? Just running a bunch of trajectories. Okay, so this is kind of my account of how I would catch a wave packet. I have a strong preference for the second one, for the obvious reasons. But strangely enough, at least mathematicians don't like it or somehow ignore it. I mean, it's not widely regarded in the community, but I think it's super cool. Whenever I try to do something else, I end up with something worse. So this is kind of a description of my research program for the last few years. That's kind of, I don't know. Yeah. Why do you work if you have something good already? Okay, so just to wrap up or finish, to show that this is really practical. And these are computations, the kind of the predecessor of that laptop is done. Yeah. It's a problem in dimension 6, cooked up sometime in the 90s to harm people who love semi-classical approximations. It's a cooked up version of Hennen-Hall's potentials, cubic potentials. It was a proposal from the theoretical chemistry group in Heidelberg to stop the semi-classical clock. And the point is, that was a bad example because you see, So it works pretty well. So the dotted line, the reference, is actually my favorite method. Does very well. And on the other hand, you see kind of the method that is more sophisticated in terms of quadratic moments, in terms of oscillations, etc. You put much more in. You see you are happy for the beginning, and then you suffer the problem of not being a geometric person, right? The usual disease, your energy starts drifting, and then everything else goes away. And I mean, you see here, half an hour, it's a coffee break, right?
It is interesting that it is the energy but not the phase.
Exactly. I think it's the energy. Might be that that mistakes in the phase come into it, but I think it deserves more analysis. But from my gut feeling, all the computations we did that we didn't like had an onset with the energy sucking. Mass and energy sucked, and then the rest went wrong as well. And I mean, here we stopped at 20. You can imagine what it looks like. This is just to show you the descent part of it. But this just becomes total garbage very quickly. And now another story. So this is now a molecule. when we did that computation, I told it to Ari. He told me, "Why do you care? It's ammoniac. Ammoniac stinks." But nevertheless, it's 12D. And the state of the affair was there was a potential energy surface that was built in Munich, and another group had done very sophisticated simulations with it. Sophisticated in the sense, kind of true bona fide tensor product, tensor discretization of the thing. That should be extremely reliable, but there were it was not really clear because the potential was formulated in symmetry adapted coordinates, so the Laplacian was not a nice Laplacian anymore. It was not clear how to really discretize this Laplacian properly, and there were two different simulations. You see the dotted ones and the green ones from a method that should be reliable, just depending on tiny twists in the discretization of the Laplacian. And then at some point, I don't know how it actually came about, but there was the idea, why not use this methods we have, the super simple Wigner type 1, because dimension is not a problem. I can do 12D classical dynamics for free, so I don't care about the Laplacian in any symmetry adapted coordinates. So I just go and we somehow, and we did. And you see, I mean, it was several hours of computation, not a big deal, overnight thing. And unfortunately, the outcome, I mean, all of us believe with all the convergent studies we did, and even more that we somehow quite democratically went in between the two previous computations, that this is rather reliable. And at the end of the day, the slope of those curves was not the right one, not the one that gives the expected physical consequences about fluorescence behavior of ammoniac. So there's no new potential being built. Kind of that dilemma I told you. I mean, and I think if this several hours of computing time had been spent right at the beginning of building the potential, life would be better for everybody. So I'm trying to push, but I do not know how to advertise with more power that these kind of very light methods get used as a routine. Just use it to get a qualitative picture. At the end of the day, if you have to bet your neck, of course I would also go for fully converged tensor method or whatever. But just to get an idea about slopes and curves, I think this asymptotic methods are brilliant. And you don't, I mean, I can do it, right? You can write a high performance proposal. Do it overnight here. And I would kind of, my mission is somehow to push that more forward. There's something very beautiful, very sound. We know about the limitations very well because we have good handles here on what the constants actually do. I think this method deserves to be super popular. Surprisingly, it is not. I mean, there are prejudices because of while quantization behind. There's always that argument, it's just classical, can't be good. I don't know, right? I mean, I have exact analysis. I can tell you the qualitative behavior of the error constants. I can tell you when it is not good anymore. I think it should be basic toolkit. But unfortunately, it's not. Okay, so more on all this stuff. Is in the review that is coming shortly. Thank you.
Okay, questions?
With the Wigner method, did you mean you just start with the Wigner equation, then you use Gaussian beam?
If you
That same thing? Or?
no, even simpler. If you put a Gaussian beam,
Yeah.
you would breathe, right? You would allow your beams to breathe.
Yeah, sure.
I don't. It's even more simpler.
Then how does this compare with the frozen Gaussian beam?
It's better than a frozen Gaussian beam because I mean the frozen Gaussian beam compensates for the non-breathing motion by redistribution of weight between and the frozen. I could have held and I was actually thinking about a parallel talk to that one. Instead of the Gaussian beams, I could have put here the frozen approximation, and I could have drawn the same conclusions. Again, by collective oscillations, I get that error, but I have zero conservation factors.
To get higher order, if you expand the phase into higher order, you can polynomial, you also get higher order.
No conservation.
Conservation. So the gain here is really conservation.
Gain is the conservation, and the super cheap thing. Just flow. You know, no linearization, no phases. It's embarrassingly simple, and due to that embarrassment, rather robust, right? I mean, with the Gaussian beams, with all that oscillations, that's quite delicate to handle. I mean, right, it's doable, you know, but it's different things. The linear is joke.
So what are the restrictions on the dimensions here? Is how do the constants scale and how high can you go in dimensions here?
You hit the constants when you do Monte Carlo like discretizations in phase space, and you hit them in the variance, as you always do. But so for the Sennenhals academic benchmarks thing, this goes as formulated in arbitrary dimensions, and we did so for the Gaussian beams. You typically get stuck around dimension 5, 6, 7-ish somehow, because then you cannot handle the oscillations anymore. With the Wigner method, we went up to 100, and we didn't really realize, and you know it became pointless because of lack of reference solutions, but you produce beautiful blocks that look reasonable without effort. It's no, so I mean you hit dimension here once you do the quadrature, but not right on spot.
Well, if there are no further questions, thank you again.
Thank you.